All right, welcome to the 136 project on pump storage hydropower. I'm Andrew Tinker.
I'm Zachary Kaiser.
I'm Joseph Silvia.
So first we'll go into an overview of the pump storage hydropower technology. So pump storage hydropower, PSH, uses low cost, excess, or unusable electrical energy during low peak times to pump water from a lower reservoir to an upper reservoir, which is stored for later use during peak demand times. The energy used to pump the water to store for later use can come from renewable sources. And PSH is an efficient method for energy storage, and storage facilities can last for many decades. So a little history of pump storage hydropower. It was first used in Switzerland in 1904, and PSH's popularity grew in the US around the 1960s. They were originally designed to be used in conjunction with nuclear power plants as a way to meet the fluctuating power demands. As loads changed, nuclear plants cannot start and stop as fast, so it helped in conjunction with that. And PSH currently accounts for 95% of all utility scale energy storage in the US. Most PSH facilities were built more than 30 years ago between 1960 and 1990. So need for pump storage hydropower technology comes from the fact that we have the demand for renewable power generation is increasing. So PSH essentially acts as a battery, and as a battery, it will offer grid stability. It's used to meet fluctuating power demands due to the variability of renewables such as wind and solar, and especially during peak times when renewables cannot meet demands. It also can provide network frequency control. And if you look to the chart on the right, you can see from 12 a.m. to 6 a.m. when demand time is low, it's charging the system, pumping the water up to the upper reservoir. And throughout the day, as the load profile increases, it starts to release some energy to help meet the demand. And if you get between about 4 p.m. and 6 p.m., you can see the peak, and that's the generation profile without the storage. And if you implement the storage technology, you could see it levels off there. So it helps with grid stability. It's going to help with generation as well.
Okay, so going over a technical overview of a PSH system, as you can see in the upper right corner of the diagram below, there is an upper reservoir, and then on the bottom left corner, there's a lower reservoir, and connecting these two reservoirs together is a penstock, which basically just allows water to flow from one side to the other. And in the middle, there is a turbine, and the turbine can act in either generation mode or pumping mode, which will be further explained in the later slides. The two most common configurations include a pure off-stream pump storage, which was explained in the previous slide. It has the upper and lower reservoir with the penstock connecting them in the middle. And then the pump back facilities, they use a dam system, and they basically open the gates, allowing water to flow through, and it uses natural stream flow rather than water being pumped back and forth between reservoirs. To go into more detail for the pure off-stream pump storage, this reservoir has little or no natural drainage catchment basin. The upper basin is filled only using water pumped from the lower reservoir. It's purely off-stream. There's no contact with any other flowing rivers or anything like that. Some of these are constructed with both the upper and lower reservoir completely independent of a natural lake, so they would basically be creating both reservoirs from scratch. The primary advantage of this is that there is no interaction with aquatic life for the most part, since they're creating the reservoirs from the ground up. The potential off-stream water sources can include groundwater, seawater, and treated wastewater. The disadvantages, they include groundwater testing and water rights investigation. The pump back facilities, these use a combination of natural stream flow and pumped water. These are typically larger and better suited for the weekly or seasonal variations. Similar to traditional hydropower facilities, except some or all of the turbines are specialty pump turbine units. and there is a reservoir available to form the lower reservoir at the bottom. And these are attractive in cases where they would like to firm up peaking capacity of the facility during periods of low stream flow. So going back to the pumping and generating mode, during pumping mode, this is when they're pumping water from the lower reservoir back up to the upper reservoir. And basically when excess energy is available on the power grid during those low peak demand times, this is when the system is able to pump water back up. If they could use either renewable energies like that they stored earlier in the day, or they can just use low cost power to do it. And generation mode is the opposite. It's when they are generating electricity by letting water flow from the upper reservoir down through the turbine into the lower reservoir. And this is done during peak times to kind of help keep the grid stability. And both of these modes have limiting factors. For pumping mode, the limiting factors include the available excess energy, the unit capability, and the available water in the reservoir. And for generation mode, the limiting factors include the demand for energy, the unit capability, and the available water in the reservoir as well. In terms of turbines, there's two types of turbine units that are typically used. The more conventional method is the single speed units, which is just a synchronous electric machine. This allows the unit to operate in both pumping and generating mode by changing the rotational direction of the motor. The reason most turbine units are still single speed units is because the adjustable speed units are kind of newer. They haven't been implemented as much, but the adjustable speed units do have an advantage because they can vary the rotation speed of the turbine. And this just provides more overall efficiency for the grid, and just it's more reliable and more stable. And as you can see in the chart below, the red part in the graph represents the single speed units, and the blue represents the variable speed units. And as you can see, it's just overall more efficient to use the adjustable speed units. However, there are some pros and cons between both of them, depending on how the system is going to operate.
Okay, so now we'll talk about energy and power of the system. There are three types of energies associated with the PSH system. You have potential energy of water due to gravity, elevation. You have the pressure energy from the total volume in the upper reservoir. And both of those get converted to kinetic energy when the water's in motion. Basically, its velocity, it's related to its velocity. And when the kinetic energy is then turned into power, and the power calculations are performed using the water weight, the flow rate, and the change in head. And the change in head is an energy per weight calculation. And so it varies for pump and turbine mode. And in pump mode, a change in head is applied to the pump. And for turbine mode, when it's generating, it's applied to the fluid. Therefore, power calculations do vary slightly, but you have to consider both calculations when determining overall system efficiency. So efficiency, talking about efficiency, the efficiency of the system is the cycle efficiency is the ratio between energy outputs and energy inputs. It's the full life cycle of the overall system, and it typically recaptures 70% to 80% of its energy inputs. So for every 10 megawatts of energy that's inputted into the system, you get 7 to 8 out. And its losses are typically found in the waterways and the pump turbine, and the losses are heat from the friction of the water when it's moving. And as you can see here, you have an overall system, which shows your useful energy and your losses. And if you look to the far right, top right, you can see the lost energy, the number 3, that's associated with the penstock. And if you look at the key, it says it's the loss in the penstock there. And it tells you that basically that's where you're losing most of your energy when the water's in motion. And that's where that heat from friction comes into play.
Okay, so before constructing a pump storage hydropower facility, there's some design considerations that need to be gone over. The key elements needed for a site to be appealing are the topographic conditions that provide adequate head from the upper to lower reservoir. And so what we mean by this is that we want the shortest possible intake, penstock, and discharge tunnel to ultimately lower our costs and our losses. We also want favorable geotechnical conditions. And so this is just related to the foundation. We want availability of sufficient quantities and qualities of water. And we also want access to electrical transmission networks and low cost power for our system. So for the system itself, there's some things that we need to consider. So the first is the head, which is just the vertical change between the upper and lower reservoir. Typically in the United States, this is anywhere from 300 to 2,100 feet. Low head projects require larger conduits to channel the water, and so that's going to lead to more money. So it's something that really needs to be considered. Flow rate also needs to be considered. Higher flow rates require larger waterway conduits and larger pump turbine units. So a cost benefit analysis must be performed that considers a bunch of different flow rates and plant sizing capacities to make sure that the project is within budget. We also need to consider the waterway, which is just the system of conduits that connect the upper reservoir, the powerhouse, and the lower reservoir. Shorter waterways are always desired because they are cheaper and we lose a lot less to friction. We also need to consider the upper and lower reservoirs. Uh, Often existing reservoirs are preferred because it can greatly reduce our costs in our overall system. And we also need to consider seepage losses from the reservoir's foundation because we don't want to lose too much. The last thing that we need to consider for the system in general is the pump and turbine selection. Larger pumps and turbines are often preferred, but they require sufficient operating head levels and adequately sized lower and upper reservoirs. We need to consider the unit size and type. So as mentioned earlier, adjustable speed units are usually preferred, but they're going to require additional components, which in return will result in a higher overall powerhouse dimension, and that leads to higher costs. So it all needs to be considered. Typically, individual pump and turbine units, their capacity range from 133 to 325 megawatts. So it's not very uncommon to have multiple pumps or turbines. We also need to consider the environmental impact of our system. So this is just issues related to surrounding wildlife and aquatic species because they will be affected. We need to consider the loss of revenue for populations that rely on the water source. We need to consider sedimentation issues, which are a result from the pumping. And we also need to consider if potential flooding of nearby land is going to cause any problems. So now everything is cost related. So we need to look at the costs associated with the pump storage hydropower facilities. So we have initial capital costs, and that's just going to include permitting, planning costs, design phase costs, construction costs, and land acquisition costs. And then we also have another major category, which is the operation and maintenance costs. So these costs pretty much just depend on the size of the project, as well as how and where the project is operated. But it's important to note that the operation and maintenance costs are usually very low compared to the initial cost.
Okay, so to give an example of a couple PSH facilities, this one right here is the Bath County Pump Storage Station. This is in the United States, and it's considered the largest battery in the world. And it has a storage capacity of 24,000 megawatt hours. This facility was completed in 1985 and cost 1.6 billion at the time. But if you compared that to the cost of what a PSH system would cost now, that is relatively low compared to what it would be. And another example right here is the Okinawa Yambaru Pump Storage Power Station, which is in Japan. And this is actually the first pump storage hydropower facility to use seawater as storage compared to like fresh water. This facility was completed in 1999. It only has a 30 megawatt capacity, and the construction cost was relatively low. It was only 30 million. compared to the previous slide, which was 1.6 billion. So as you can see, as the capacity goes up, the price definitely goes up as well.
Okay, so to summarize our presentation, so there is a vast need for integrating renewable energy systems more into the power grid. And PSH is one of the most efficient alternatives for energy storage systems. PSH facilities also last for decades, so they offer longevity as opposed to other storage systems. And they have one of the lowest carbon footprints for energy production. They account for 95% of all utility scale energy storage in the US, and many design, cost, and environmental factors must be considered before moving forward with the production of a system, as well as including talking about the main components. So we have an upper reservoir, a lower reservoir, penstock, transmission system, connection to the grid, a turbine that operates in both pumping and generating mode. And then the turbines can be configured for either single speed or adjustable speed. And thank you for your time.